Okay, we're going to begin the 6 weeks speaking of waves. A wave is a disturbance in the medium that carries energy. There's your key point right there. Know that waves carry energy from point to point. It can also be a wiggle in space and time. You can define it as a simple harmonic motion, which is, if you've seen a clock with the pendulum, it goes back and forth, back and forth. All waves, all mechanical waves have to have a medium to travel through. A medium can be a solid, liquid, or gas. I'll let you think about which one you think the waves travel through the fastest, and then we'll talk about that in class. A pulse is a single wave created, so just one single wave. Two types of mechanical waves are transverse. The key is the transverse wave is perpendicular to the direction. So you see right here, the wave is going this way, the direction's this way, but it's moving up and down. So those two lines are perpendicular to each other. Some basic properties you need to know: amplitude, wavelength, frequency, period, and velocity. Know what these terms mean. It's because we will be using these in class. This is a picture of a transverse wave. Couple key parts: you have your amplitude, distance from crest to nodal line, or from trough. So this could be amplitude or that, as long as you measure that distance right there. Your crest, the top of the wave. Trough, the bottom of the wave. Wavelength, in this case, is from crest to crest. The node is where the wave crosses the nodal line. This is called the nodal line. This point, which isn't on this graph, would be an antinode, where they do not cross. You will have to label all these parts on quizzes and your tests, so be familiar with them. Second type of mechanical wave is a longitudinal wave. It travels the same direction, so you can think of this as being parallel. So if the direction's that way, the motion of the wave is that way. They travel the same direction. The parts for a longitudinal wave: you have your compression, which is where it's all bunched up together, your rarefaction, where it's spread out, and then the wavelength. Those are the only three parts you label on a longitudinal wave. Here's a practice question. See if you can get this one correct. We will go over these in class. Now we're going to look at how to calculate velocity, frequency, and period. This is the math portion. Here's your equations. Frequency, which is the number of waves per unit time, waves per time, it's 1 over the period. The period is how long it takes for one wave, so time and over frequency. Since these two, frequency equals 1 over period, and period equals 1 over frequency. If you look at those two terms, you can see these two are inverse of each other. So here's some examples we're going to go through. I want you to practice these on your paper, see if you get the same answer I get, and we'll go over these in class. Here's the velocity of a wave. The equation: velocity is wavelength times frequency. This is upside down y. It's lowercase lambda. That's wavelength. Here are your units. Here's some examples. So wavelength of a 340 hertz sound wave, the speed is 340. So plug in your equation. Velocity equals wavelength over frequency plug in your velocity of 340, your wavelength, what you're looking for, and your frequency of 340, and you should get wavelength equals 1. Another example, you're looking for speed. Use the same equation, see if you get the same answer. This one's looking for a frequency. You should get an answer of 5 Hertz. Now here's a question that I want you to look at. Think about how wavelength and frequency are related. We'll get more in depth in class. See if you can answer this. And also, do not forget to take the quiz on the Open Campus Moodle site. It is due Monday at 9 a.m., March 3rd.